Yeah, it looks like the whole, I don't know if you're ready to the left or not. Is it left off the screen or? I believe it's off the screen. Okay. Yeah, it is. So I'll let you play with it a little bit to figure out what you need. I don't know, does anybody, while we're just working on making sure that the resolution, Eric's fixing the resolution here, any questions that are burning people? Yeah.
Some of you may run into this recently. A friend of mine has an XP machine, and I was looking to put a Linux distro on it that would be close enough to be comfortable. They're marginally savvy. Okay, they're willing to poke around. My choice was going to be Linux Mint. Primarily because it tends to have all the nice support for sound and whatever. I mean, literally. They do two things. They play solitaire and they, surf the web with an occasional document here and there for their printer. So, is there any other choice that people might feel is better, or some other things they might think about?
I'll just say that I went through this whole exercise for a couple of church computers recently, and I ended up using Linux Mint with the Cinnamon desktop, and so far so good. People don't seem to really notice much difference.
So I've heard great things about Mint. I actually installed it for my in-laws because they go to a couple websites, and that's pretty much it. And to the point where I actually put hot buttons across the top of Firefox or Chrome or whichever the default browser was, Iceweasel, whatever, so that it went to their AOL account and logged them in so they could see their email. And then they had a link that said USAA, Navy Federal, and I forget what their commercial bank is, so that they could click on one of those three, because those are the 4 places they go, and that's it.
Yeah.
And they don't even do documents. So I had that set up for them, and to the best of my knowledge, they don't turn it on very often. When they turn it on, they can do what they need, which is the important thing. So I've heard great things about Mint. I sent Mint up for my in-laws, and that seems to be, for whatever reason, whoever their PR person is, if you search engine, XP replacement or Windows replacement, Mint is the #1 hit that I found. So that seems to be good. And I think it's Debian based, if I remember correctly. So,
very good.
That's it. Any other questions? So Denny's back this month for Internet in a Box. And so afterward, you don't need to scoot out right away, do you?
I got to hang around.
Great.
I need help.
So he needs help. I was going to try to help. Unfortunately, my life has gotten turned upside down recently, and I can't even find an extra 2 hours to take a look. Based on what he tells me and what I've looked and a little bit of research I've been able to do online, since I've not been around, it looks relatively straightforward, so that, if you know how to install an OS and you know how to do some web content, which is basically where you copy stuff into for the web server, it should really be that easy to help him out there. So anybody who's interested, and maybe we'll even be able to kick off the box and take a look at it, so people can get a look at this afternoon. But he spoke about it last month, and it's basically, specifically in Haiti, making internet content available where there is no internet is the easiest way to explain it.
That's it, in a nutshell.
So, of course, there's a little bit more behind it than that, but that will help people. Next month, looks like it'll be Peter on OpenShift for developers, how to use OpenShift for development purposes. And so
speed up your development. Yep.
And then we'll figure out July on from there. I've not had an opportunity to talk to Jason. I did see Jason is here to let us in to know, come July where we will be meeting, or if we're going to need to find a new place.
So we're here in June?
As far as I know, we're here in June. I think they're open still in June. I don't think they're getting kicked out then. I have. It would be tight as heck at my office at the town center, but we may be able, I can try to figure out, I think we only have Actually, I think we had 20-some chairs that we could try to configure and move around. We probably have to do it in the open space because I don't think any of the conference rooms hold 20 people at this point. But I will take a look this week to see if that may be an option if we need. Pete?
We have an office, Deloitte has an office in McLean, I can inquire there. I know there's at least one training room.
Okay.
That's about the size of this room, maybe a little bigger.
Okay, I appreciate that.
So I can find that. Security,
Yep.
physical security might be weird, but also I can find that.
Okay. But yeah, so we're not officially under full look for it yet, but that may be coming, and I may end up checking out the library at Reston again, which we have used in the past, and if we need to use that as a holding pattern, we may do that. So just be aware, we'll see stuff on the list as I learn more about what space options.
How about the community center on the other side?
Yeah, no. Getting in there, first of all, it costs money. Even though I'm in District 5, so I do have priority over non-District 5 people. But also, they have weekend classes and whatnot, so getting in there. I have not looked at their schedule. I just know it can be difficult to get in there. Because I had looked at the one at Lake Ann. The issue that you run into at Lake Ann this time of the year is the farmers market's going on. So there's 2 community centers in Reston. There's one on the north side and there's one on the south side. But yeah, Colts Neck Road and South Lakes or what have you, Hunter Woods is it's hard to get in there. But I will double check just to make sure. So with that, a while ago, after a meeting, Eric stopped me and said he was interested in talking about development, cross-compiling, virtual machines, and this was scheduled, and then his life got complicated for a while, and so we are now at a point where he is able to come and speak and present. I tried to send the slides to the list, forgetting that they were too big, so they were rejected. I will probably either put them up, figure out how to upload them to the website so people can get them from there, or at least compress them and make them available that way. But I will make the slides available to everybody also.
Do you know what the size limit is? Because surprisingly, the LibreOffice version is smaller. Yeah.
Yeah. Yeah, and I think it's by default, it's like 40 or 60K, it's not that big. And I was trying to approve it because I have the ability to approve and send large objects if I want on the list. The problem is I let the spam just roll off. So I was on my phone when the message came in and I forwarded it, it got held up. And I thought, oh, maybe all the stuff is rolled off, and it hasn't. So it was not at the top of the list or the bottom of the list, and I didn't feel like on my phone scrolling through 100 messages to find it. I figured when I was on my larger screen, I would be able to handle that. So with that, I will now. Oh, and I do want to, before I turn it over to Eric, is to thank Peter for month in, month out being our videographer. Hello, everybody out there who's paying attention. So, with that, I'll turn it over to one person. Who is it? So I can say hi and give a shout out.
You don't know.
It's not Doug.
It doesn't say.
It doesn't say.
Let me find the out here.
Oh, so it must be one of those people.
Should be David Green.
Oh, Daniel Green. Dan, you should be over here. You should not be slacking on your back deck that you cleaned recently. And now everybody knows that some guy named Dan Green on the internet cleaned his deck and sealed his deck within the last 6 weeks. So with that, Eric, I'll turn it over to you.
Cool. Yeah, so thank you. So I did try to send out the slides. I was a little slow in doing that. Didn't send them out last night. They are available if you want them after the presentation. One thing I'm going to point out, and it's also in the slides, but towards the very end in the references, is all of these demo scripts that I'm going to be doing today are available on my OpenDev repository on GitHub. So here's a link. It's just at github.com/emhj/opendev. And then underneath it, there's a directory called QEMU. and then workshop 1. So I was hoping to actually make this more of a workshop feel where people could, play along, I guess, and go at their own speed and play around with the different things. It's just a series of scripts that walk you through going from start to finish, running a QEMU machine with a very recent Linux kernel, and building your own root file system as a fake SD card that you could actually burn to a real SD card and then plug it into an actual device. So with that, I'll switch over to the slides. So the title of the talk is Cross-Compiling Emulation and Virtualization, but really this is more of a, at least in my mind, a brief introduction to embedded Linux development. The motivation for this talk I'll cover a little bit later, and just go over the abstract just for reference here on the first slide. So quick background about me. I'm a software developer. I came out of Virginia Tech, sporting logo shirt here. Been 4 years working in the industry right now, the defense industry. 2 years specifically focused on embedded development. And 7 years or so just playing around with Linux and doing various things. As I said, motivation for this talk, it's developing without hardware is the main focus for me. Oftentimes I find myself in a situation where I need to be developing, but I don't have my hands on hardware, and I'm not going to get hands on hardware for quite a bit. So usually I have to come up with a way to either emulate the hardware or hopefully leverage something that already exists, such as some virtualization technology that's already out there that I'll be talking about today. Another motivation for this talk is just teaching basic virtualization concepts. I don't know how many out there are familiar with them. I assume a decent amount are, but not everyone. I'm also interested in teaching people how to build open source software. If you are kind of new to the game, and I would consider myself new to the game, I didn't realize how, but there's like a methodology to it, and it's very formulaic. So I'm just going to kind of shed a little bit of light on what that formula is, and I guess the conventions that some of you who've been in the industry are working with Linux a lot longer are already familiar with. Also, I was interested in teaching people about QEMU, what is it, and how you can use it. I also wanted to briefly show how building your own Linux distribution is really just an iterative process. It's actually kind of rewarding because it's a bunch of solving little problems. It's not too difficult. So for the goals for this talk today, I just wanted to cover do-it-yourself embedded Linux, just kind of introduce basic concepts. Go over some cross-compilation theory. What is it? What is cross-compilation? What is compilation, for that matter? Then move into virtualization with QEMU and actually get into some live demos covering just running some basic things with QEMU and a very recent Linux kernel. And I'll actually be working with the 3.14 kernel. And then finally, I'll touch on building your own Linux distribution and then a project that's out there that's making this incredibly easy to do. So I just wanted to kind of spread the word. So do-it-yourself embedded Linux, I mean, really Linux started as a do-it-yourself project. For those of you familiar with the backstory, Torvald sent out an email basically saying, hey, I'm going to work on this small little project. Yeah, it's not going to probably be that big or go anywhere, but if you're interested, send me an email. And then, 20 years later, it's now got a big following and used all over the world. But oftentimes, do it yourself kind of means do it by yourself. I don't think that has to be true in this case. I think we have a nice community here, so feel free to ask questions. Always happy to help out and answer. So today I'll just talk about, like I said, a couple of tools that'll help you with your own do-it-yourself projects at home that you might be working on, including creating a root disk and populating it with basic core utilities. And I guess the little mantra, be persistent. Failing is an opportunity to try something new. Yay, motivation. Just continuing on, so the motivation for this talk, again, was how do you kind of test Linux? In the old days, it was really, even this is still true in some environments, is you build it, you kind of update your bootloader and hope for the best, press enter and see, did it crash or not? Let's try again. and tweak something and go back to the drawing board. But when you want to build something that will run across a lot of different platforms, say you're modifying a Linux kernel, for instance, or adding a new module, you can use virtualization technologies to test that well in advance. There's a plethora of devices that are out there that you can compile for and then run on to test ahead of time without even getting your hands on hardware. And that's really what I want to emphasize today. Well, a very important thing to keep in mind is virtualization is never a perfect substitute for hardware. In my own work, I have found some interesting things, particularly when it comes to vectorizing some operations. So recently, I was working with a device that has an ARM chip with a neon vectorized processor. And when you run it on the actual hardware, you can see incredible performance gains. But when you run it in the QEMU world, not so much. In fact, it degrades back to its C variant, which is kind of interesting. So there is a caveat with virtualization. You should always actually, if you can, run on real hardware. But it's a good staging and good testing ground. So I don't want to undercut myself too much here. So first, I want to cover some very basic theory that I think most people here understand, but just in case, I wanted to answer at least how I view what a computer is. And you can compare it with your own notes, what you think about it. To me, a computer is nothing more than a device that has instructions and memory to operate with those instructions. And oftentimes, those instructions are referred to as an architecture type. There's a lot of ways to model a computer. Today, I'm just really interested in focusing on one, which is the Turing machine. I think it's a very elegant concept that you can explain not only compilation, but cross-compilation very simply. But there are other models out there as well, but we can talk about that in the open discussion. So what is a Turing machine? For those of you that don't know, it was developed by Alan Turing back in the 1930s to solve a problem that David Hilbert, a mathematician, proposed for how do you answer or how do you mathematically rigorously prove the answer to a decision problem, a yes/no problem. This is I cannot pronounce that, but someone who speaks German might be able to.
Entscheidung.
Okay. Problem. But he developed this, and what's kind of interesting is Alonzo Church, in parallel, working on the same problem, developed something called lambda calculus, which is kind of interesting. These two big things came off of this one problem that they were trying to solve. But eventually it resulted in the Turing-Church thesis that von Neumann used when he was developing his model for the von Neumann architecture. So informally, a Turing machine, what is it? It's basically a machine or device or some abstract thing that manipulates symbols on an infinite tape. So something that just has infinite bound, that's divided into blocks, and on each block has a symbol. And in the next slide, I'll cover a very simple example. So the symbols, they are derived from a specific language. And if we think about what a computer is, the language in this case would really be the architecture, the instructions. So these correspond to instructions. They're often represented in a table, sometimes referred to as the action table or transition table. And those of you who are familiar with state diagrams or state machines will recognize this concept. Typically, you'll also have a special symbol called the halt. In my example, I don't. This is just going to go on forever. But there's often a halt to stop the machine. And what's really interesting about the Turing machine is that it's the first concept of really a stored program. And it's a fundamental jump and a very important concept in computer science, especially when you want to prove certain things as far as computational complexity. The NovaLug design. Is there any way to? Is it glaring on
It's all the flashing keeps changing the light.
Yeah.
Facing you out.
Two. Is anybody plugged into the township? Watch this. Here we go.
Hey, look at that.
Wait, where am I?
Why don't we roll behind you?
So the tape and the Turing machine example corresponds to memory, is one way to think about it. And the machine itself, you have this head that marks where your current position is in memory, and the next instruction to go execute. So a very basic example is constructing a sequence 0 space 1 space 0 space 1 space 0 space 1 space, etc., and go on infinitely. And I have to admit, I'm taking this example from Wikipedia. I didn't bother to come up with my own, but I think this is a simple enough example for most people to grasp very quickly. And so the action table, in this case, you have these 4 states, S0 through S3, and I actually have a typo there, that should be S0. But basically in each state, depending on what the next symbol in the tape is, in this case, for this machine, it only expects one symbol, and it doesn't actually care what that symbol is, but in this case it's just going to be blank. And then it performs its action, and then moves to the next state. And then in that state, it moves, it does its action, and then moves to the next state, and just kind of repeats infinitely. So you can see the state diagram kind of models this action table here on the right-hand side. And basically, at the start, if you can imagine, this is the head, and the kind of grayed out thing is the action that will happen after S0 takes place. So the head will move to the right. Well, first it'll actually print a 0 on the current block that it's on. It will then move the head to the right, and then it will transition into state 1. And then it will just keep working its way down the tape in this manner. Is there any questions on what's going on here? If I'm not making sense, let me know. I don't see anyone out there. So I thought this was a pretty simple example for a Turing machine. And in this case, I kind of think of as the operations, kind of as the instructions of the language. So with that, I can now start to work with the definition of, or on a definition for compilation. What is compilation? I think in the most general sense that people use the term, it's just taking a high-level description of a language or something of a program and translating it into a language that the machine can understand after doing some validation. And the purpose of a compiler is to detect invalid programs and also to detect valid programs and translate valid programs. In the Turing machine example, compilation really kind of corresponds to creating that action table. And it's using the same language or architecture of that Turing machine. And I would kind of compare, I'll jump back here real quick, that if you were to imagine if these instructions in this language are English, for another machine they might be Chinese or just another language altogether, and that could correspond to a different architecture. That's how you can think about it. So cross-compilation on that note can be thought of as a Turing machine using one particular language, creating an action table, using the language of another Turing machine. So that would be taking the English instructions and building Chinese instructions out of it. And that's how you can kind of think about what cross-compilation is. Is there any questions on that? So what's emulation and virtualization? I'm going to say that these are my definitions, so I don't know what the real definitions of these terms are. But here's how I think about them and how I'm using them in this talk. They're very similar, but I kind of think of as emulation being a subset of virtualization. I think of virtualization being a much more general concept. Emulation strives to provide a very high fidelity representation of a machine. And that is to be as realistic as possible, including timings, including even these vectorized operations that I was talking about before. Whereas virtualization, you got a lot more leeway. It's kind of fluffy, it's kind of vague. What it really just means is it's synthetic in the sense that the timing could be way off, but you don't particularly care because you're more interested in the end result. It doesn't matter how you got there. That's how you can think about it. But in either case, you can use these things to simulate functionality of another machine. And in this case, keeping our Turing machine example going, you can have a Turing machine be programmed to act like another Turing machine. And this is known as the universal Turing machine. And that's really at the core what is going on with emulation, and even really just virtualization in general. So some examples of full machine emulators that some of you may be familiar with are QEMU, or VirtualBox, or VMware. But there are a lot out there in addition to these, and I don't know how many there are myself. So today I'll just be covering what is QEMU. It stands for the Quick Emulator. It's a free open source platform emulator. It supports a lot of different machines. And there's kind of two different operating modes that you can work in with it. There's full system emulation, which I'll be talking about today and I'll be focusing on. And then there's kind of user space emulation, which is it translates machine instructions on the fly. So they don't actually have to spin up a network device if that's irrelevant to your process or something like that. And the first public release that I could find was back in 2003, just for historical perspective. So what are some of the targets that are supported for full system emulation? You've got your basic PC, the ISA PC, you've got the G3 Power Mac, ARM Versatile Baseboard, Spitz, Akita, Borzai, Terrier, Tosa, PDAs. I mean, a lot of these devices I've never even heard of, seen, or played with. But these are actually just a very small set. I found out more recently that groups such as Xilinx and Monaro have their own forked repositories of QEMU. And some of them try and push back upstream to the main development, but they have their own flavors that you can go play with that are newer and support other operations or newer machines. So for today, I just wanted to play around with the ARM Versatile Express development board. I kind of just picked this arbitrarily, but for me, I've been working a lot recently with ARM devices, mainly because, at least as I understand it, the ARM architecture is got a very good flop to watt ratio, which would mean that it's very computing efficient in terms of power. And this is why it's very popular among the embedded community. And so the Versatile Express is actually just a development board that ARM Holdings itself provides. It's kind of expensive, so I did not get a chance to buy one and actually put it on the table here to play with, but maybe for a future talk or something. So some of the basic hardware that supports got a quad-core A9 processor, 1 gig RAM, SD card, even has graphics, keyboard, mouse, whole shebang. Really, it's a basic machine that you can use to play with. I was curious about the Versatile Express machine. That's actually a baseboard, and you can layer other boards on top of it to provide more functionality. If any of you have worked with Arduinos, it's kind of a similar concept where they have different modules that fit in on top of the board. So we've got some links down there where some people talk about it some more. So this is just a kind of a reference slide for anyone who wants to review the slides after the fact and wants to kind of build the software as I've used it in this demonstration and this presentation. I've just kind of provided this as reference material. I'm not actually going to cover it, except with, I guess, one exception, which is in the open source world, the GNU coding standards kind of mandate the configure, make, and make install. Those are your basic commands to run whenever you run into a open source project. I think a lot of projects out there have adopted this model, although newer things such as projects that support CMake or SCOM, they've got a little bit of a different feel to them. But this is the Auto Tools way of doing things. So those of you who are not familiar with building open source software, when you get a new software package, typically these are going to be the first three things you do: configure, make, install. So now we start getting into the basic demos. So I'm just going to give a brief introduction to some simple commands that you can run, including just if you run the QEMU system ARM command just by itself, I find this kind of not intuitive whatsoever, and they've changed this in a recent version. But it actually spins up a machine. Yeah, I know. That's what I find.
Yeah. You can't see it visible. Yeah. Can you swap, change black and white?
Oh, geez. Maybe.
You're using
Yeah.
or something?
Yeah, let me see if I can update my X resources and see if we can get the color. Jeez. I guess, what is it, all S?
Yep.
We can give that a shot. Probably I'm actually using UX term for UTF-8 days. We'll see if that works. The text, we may need to change the text color. Let's see if we do that. That might just be, or not work at all. Let's see, I think I have GNOME terminal on here, and so we can put it like that. Of course, I changed those colors, but I can edit
You just
that.
right click on that, go into profiles, yeah, there we go.
Yep, and then colors.
Use the built-in.
Yeah, yes. See this a little bit better?
Absolutely.
Is the text size big enough? Then we can get a little
For the
bigger.
video, you definitely could do this.
All right. Let's use a custom.
No, go down,
So we want to bump this up.
I'm liking that italic myself.
Ah, yeah, that may be a little too big, but okay.
Well, I'll bump that back. Let's go.
12.
We want them all.
All right. 12. There we go. I am going to use Teams.
Now can we move that wire?
Oh, jeez. Here, I will. Yeah. So if you were to actually check out the repository, you would find it under OpenDev QEMU Workshop 1, as I was saying before. And I'll just briefly go over. I kind of organized this into 4 directories: Demo 0, Demo 1, Demo 2, Demo 3. I've got a data directory, which actually is just, it's not checked in, but it's just storing a pre-compiled Linux kernel that I just copied over into this directory. Generally in Git, just as a brief background, you don't want to check in giant binary objects with any version control system, mainly because if you do a difference between 2 binary objects, it doesn't make any sense most of the time. So anyway, that's not checked in, but I do have instructions in the slides for how to build your own. I've got a basic README, and in each of the directories, I have a README. And in this particular demo, I just kind of lay out the commands that are supposed to be run. So going back to the first example,
And
you run
you can't sort of see that.
You can't see it. There. If you run the basic example, it actually starts up a machine, and I find this very not intuitive, and it changes to more recent versions. They most recently changed it in the 2.0 series that came out last month. But if you were to build the software as is, and this, as I outlined it in the presentation, you would see this functionality. Eventually, this machine will just crash because there's nothing to run. I haven't told it to run anything. So there you go. It just crashed. So some other basic commands that were, of course, this is going to be really awkward. What if we do it like this rather than full screen? There we go. So that's probably there we go. Is that easier to see?
Yeah.
Maybe?
Peter cuts his head off.
Yeah.
That didn't work very well last time.
So some of the other, one of the first things I do is the mhelp command, because I kind of want to see what machines are available. And this gives you a brief list of what are the supported machines that are running. You can actually see what the default machine is that was running before. It was this ARM integrator CP thing. that just went off and executed by itself. I've since changed it to be none. This is the default. So you'll get a warning that, hey, I'm actually running a machine. That makes sense. But today, we're just going to be using the vExpress A9 guy, which is this ARM Versatile Express for the Cortex A9 processor. So I'm going to cheat and look at the README and figure out some of the other commands I was supposed to run. Oh, that's right. So when you run QEMU, it actually starts up a VNC server by default. And what we can see, if we open up a VNC server, or VNC client rather, on that, we get a little display, of course, since I'm not running anything interesting or something interesting to look at. But we'll see that a little bit later. But you can disable this for those of you who don't care to use the VNC client. You can actually disable it with just the no graphic option. And in fact, I often will run it with no graphic and a monitor PTY.
Are these double dashes for monitor?
What's that? No, actually, QEMU has the weirdest set of instructions I've ever run. They don't conform to GNU long options, and they don't conform to regular Unix options. They just kind of do their own thing. It's kind of interesting. But the monitor is kind of interesting, if I can get to it before it crashes. It provides you a prompt to kind of look into the machine itself and see what the state of it is and what's going on. Of course, it's got its own help menu. Of course, it just crashed on me. But we'll look at that a little bit later. Gotta go kill that process so I can get my terminal back. We'll take a look at that a little bit later and see some of the different commands that you can run to take a look at the QEMU model itself. So going back to the presentation, your brief introduction to QEMU. I guess a couple of things I didn't cover. You're not running a monitor in a separate super terminal. The monitor, I believe, will run on standard I/O by default, although I actually tell it to run on standard input/output a little bit later in the presentation. But if it is running on that, you interact with the monitor using Control-A, similar to Minicom for those of you familiar with it. And the basic ones that I use are Control-A-H, help, Control-A-C, to go from the QEMU monitor itself back to the console so I can type commands back in. And then finally, Control-A-X to kill the machine itself. In fact, I'll have to use that quite a bit in the demos today. If you get the demos off of GitHub, you'll also have to run the Control-A-X command quite a bit to kill the QEMU process. So again, I put in a slide here for reference for those of you who are interested in doing it later, how to build the 3.14 kernel, which I believe was released like 2.5 months ago, for the Versatile Express platform. If you actually had an actual board, you could just take this kernel and run it on that board, which is pretty cool. I'm assuming here that you have a cross compiler already. Most distributions actually provide it for you. Found this out recently. And in the references section at the end of the presentation, I think I have 2 commands that show it for Fedora and for Ubuntu, but that I think it applies actually to other debian systems as well. So the first question that probably comes to mind is, okay, so if you were to get a kernel, how would you spin up QEMU with that kernel? And so that's what the next demo starts to cover. So I'm kind of saying you need to have a kernel already existing and put in the data directory, as I showed before, for these examples to work. So if we go back and change over to the other demo, I have a series of 4 scripts that loosely correspond to the presentation. Actually, I have more information in the GitHub repository than I do in the presentation, just because it'd be kind of dull if I put it all in the presentation. So basically, the first script will just kind of run the QEMU machine with the precompiled kernel, take a look at it in the VNC server, and see what that looks like. So we go ahead and run it. If we look at what the command is itself, all it is I'm specifying the machine, the vExpress A9, as I said before, and I'm adding an extra parameter called kernel, which is just pointing up over to the data directory and that compressed image that I had before. And so it's actually started up the kernel, and we can go peek at it using our VNC client from before. And we see, hey, there's now a little bit more here to look at. We've got the Tux logo. But nothing else is really going on this machine either. So let's make something happen. First, I guess I'll cover how to daemonize the process. For those of you who are interested in scripting or creating test beds, I'll call out the daemonize parameter. It's pretty useful if you want to start your machine and background a couple of GME processes. I'm not actually going to run that here. That is in script 2, I believe. In script 3, rather than having to connect to it with VNC client, I've listed out here some parameters to actually run it on the console itself. So if we look at the script 3, actually this is a VNC client-based one. So if we want to see a little bit more information, and we go start up our VNC server again, we actually see a lot more text. It's actually telling the kernel, hey, please go dump your console output to a specific device, and that device for this particular board is the AMA 0 guy right here. So that's all that was. But going back, let's run script 4, which will actually show all the output in our terminal. And I'll rerun it again. I'll actually have to reset the terminal because QEMU has a horrible way of eating the terminal. But if we rerun it, we can watch the text scroll by, and we'll see, oh, there's actually a kernel panic. It's barking on us because we haven't given it enough information to actually boot. And you can see here, there's this, please append a correct root equals boot option, so that the Linux kernel knows actually how to spin up and start. So I have a slide here just kind of outlining the exact same analysis. And there are really two problems here with this example. There's no root file system. There's actually no real device to mount. Even though it says there's this int block 0 guy, it doesn't actually have a driver to run it, even if you somehow connected a device to it. So we're going to go ahead and go solve that using QEMU to exit that. So briefly, I'm going to cover what happens on a Linux initialization and what's actually a root file system. So in Linux initialization, you can actually do whatever you want at startup. You don't have to do what you're told. You can configure it to do whatever you want. And there are a couple of ways to do this. There's the root equals parameter, which will specify a particular device to go start up with, and it has an optional init parameter. I guess a init parameter lets you specify, oh, I want to go run a shell, or I want to go run a program I customize for this machine, or something else. But it defaults to sbinit, etzinit, binit, and binsh, for those of you who are familiar with what that is. Other Linux initialization includes the initial ramdis, the initrd, which I'm not going to really talk too much about. And there's also this other thing called init ramfs. But I encourage you to look at the early user space link here at the bottom that explains all this. And it comes up quite a bit in the at least the projects that I deal with. That I would call it out. As far as general Linux file system layout, for those of you who are unfamiliar with it, we've got bin, root, dev, etc, home, initrd, lib, lost and found, mount, proc, root, sbin, sys, temp, user bar. It's a lot. But I'm not going to go over all these in details. I've, again, made this more as a reference slide for other people. The crucial ones that you're going to typically have are going to be your etc, your bin, lib, user, and var, and sometimes sys and proc.
Probably dev 2 hours.
Yeah, and dev. Oh, yeah, definitely dev. Sorry. That's a good point. Yeah, you're definitely going to have dev in there as well. So the second demo, I'm going to walk through building a very basic root file system and how you can create an SD card just as a file on your disk. and how you can actually mount that and interact with it. So you can build something that you can burn to an SD card, which I do almost on a daily basis now. So going back, change directories. I've kind of got this stuff here already, but I'll go ahead and remove a couple of things. So there's this strange C directory that's part of my OpenDev repos. That's all that is. But anyway, so if we look at script 1, all we're doing is creating a test image, and QEMU provides a tool called QEMU image to do this. And it has a variety of formats that it can build. For those of you who have looked at VirtualBox or VMware, they have different disks that they support, including QCal2, which is the QEMU copy on write, iteration number 2 device that is supported. And that's actually coming from the QEMU world, which I think is kind of interesting that it's supported there. In this command, all it's doing is creating a raw file. You can almost do it with just DD as well, that creates a basic test image. There's something in this that's actually just pure zeros. It's not very interesting. So in the second script, what we do is we'll format it with a partition type. We're going to format it with just ext2. We're going to create a mount point for it. Mount thing, create our own hello world init process, because I told you could run whatever you wanted, so I'm going to do it myself. And then finally, copy that into Etsy init and boot QEMU and make it run hello world. So script 2 will just go ahead and run. Does require mount privileges. Let's see the. It'll actually run, but it's so fast, it's not terribly interesting to watch, is it? And so all this program is doing is hello world.
So you actually have an option that will not require root. That's called guestfish.
What's that?
Guestfish,
Guestfish.
which allows you to basically use the space, manipulate your images as if they were mounted.
Ah, that's
So
excellent.
you're completely off root.
Sounds kind of similar to Fuse, which I haven't messed with enough, but it's the file
No.
user space, not at all. Okay, good to know.
Yeah, Fuse is a file. Guestfish is a tool around that lets you to manage and work inside the images. Fuse is like a file type,
Oh, cool.
more like
Okay.
FS or what have you.
Okay, so you mean file system type?
Yeah, file system, yeah.
Gotcha. Okay, cool.
Yeah.
Good to know. I will keep that in mind. Yeah, I get tired of typing in sudo all the time, having to enter in my password. So then, script 3. This is actually a bit of a trap. I do this a lot in my demos, but all I'm showing is how to create the drive itself. But I left off one crucial part here, which is the root parameter that I was talking about before. So if we look instead at script 4, you can see that I've actually added the root parameter so that we can boot up and watch our hello world program run. So rather than bore you with the process, I'll just go ahead and do it.
You said
We
you
can
didn't have
see-
the driver for it, so you didn't add the driver.
What's that? Well, before, the drive that was supported was NTD block 0. So I guess I should probably go run the other one. So if we run script 3 first, rather than script 4, and the only difference between this script and the previous one that I had run, not the script 4, but the one from the last demo was, I've added a new parameter for drive. And that'll actually specify to QEMU, go use this particular file.
So your
That's the
kernel
customer.
reported they didn't know the driver
Correct.
for the device,
Exactly.
and you didn't change the kernel.
That's correct. So we'll go ahead and run script 3 and see what it says. So there's actually an MMC device already on the board. So there's a specific driver for it, the MMC
So
block.
it's a different device, right?
That's right. And so what I was going to say is the NTD block 0 is not used in this example at all. In fact, it's not even used by this machine as best I can tell. There's no way to tap into it unless you actually build in that support for the driver, as he's pointed out. So in this case, the kernel panics, right? Because it knows that there's a device there, but it's not told to go use it. So all the next script was doing, and here's the QEMU monitor. I guess I should tell you a little bit of these commands. So it's got a lot of different things that you can run, including stop, snapshotting. I like to peek at what the devices are. So there's this input queue tree, which will list out all of the devices of the QEMU machine itself and what they're mapped to. So you can tap into it and play with them. There's a quick command. Yeah. And then if we look at script 4, using the fact that it was the MMC block 0 device that came up, we can now specify go use that device as our root file system. So what I have done is taken the Hello World program itself and set it to a common path for the init file, or the init process that when it walks through and says, does this file exist? No. Does this file exist? Yes. I'm going to go run that then. So I'm tapping into that and using that to run Hello World as my initial process. I guess for posterity, I'll rerun it and show that we don't get that kernel panic of not having a file system to go run. We get a different panic, which is saying I've attempted to kill the initial process. So it's still not that interesting in an example. So in the slides, I kind of cover this in a little bit more depth. So if you wanted to go do this on your own at home, kind of put all the text here that explains what's going on, including the little, don't forget the root parameter, as I said before. So, how do we make this example a little bit more interesting? For those of you who don't know, and I'm sure most of you do know already, the new core utils are bundled with almost every single distribution out there. And they provide you things such as like CP, LS, mounts, even I think init, and a few others that allow you to interact with your system. BusyBox does something very similar, but using a smaller footprint and a different libc. Is used more often in the embedded world. And for those of you who like to hack your Android, there's actually a BusyBox app you can install and play around with the shell on the Android itself. So this slide covers how to build BusyBox statically. You don't need to add any libraries. And for this demo, I didn't really want to go through the process of building an entire distribution start to finish. So that would be very boring. So demo 3, all I've done is pre-compiled BusyBox already, as I said. I'm going to go ahead and get rid of that test image because our scripts will rebuild it. So in script 1, all I'm doing is kind of making that basic root file, the file system tree, as I discussed in one of the previous slides. And then I actually take BusyBox and set it up such that you can use it inside of QEMU itself. And BusyBox has this interesting notion that you type BusyBox and then the command that you want to run. But if you don't want to have to keep typing it, you use symbolic links with the name of the link being the command that you want to run. It's just pointing at BusyBox, and it will do it for you.
Does it have to be symbolic link?
Yes.
Can I do a hard link?
I believe it has to be.
You can use a hard link.
You can use a hard link. Okay, I wasn't actually sure. I've always used symbolic just because, but I guess yeah, you could use hard links. But anyway, this script all I'm doing is setting up a basic SD card that does the same thing. And if we were to mount this thing, we can actually see. We can go take a look at what I've built as far as the SD card goes. And all I've really done is set up a couple of things inside here that point to BusyBox, some very basic commands. But one of them is init as well. And so BusyBox actually provides its own initialization process that you can tap into if you're building your own distribution. so you don't have to do it. And it provides a System 5 style init process, but you can easily cross-compile System D and put that in place as well. So let's go ahead and run that example. So the first thing that we'll notice is this is the exact same script as the last script for script 4 and demo 2. Well, what we're going to see is that init can't find any devices because we haven't actually, you can either build devices, and I was just going to sit here and do this infinitely, so I'm going to go ahead and kill it. You can't find any devices, and those devices actually exist, but they are part of the dev tempfs system that's inside of the Linux kernel itself, and you can mount this just using the mount command. And another thing that's out there is the proc system, and that's also a temporary file system. That's also something that actually needs to be mounted prior to the dev tempfs system. Otherwise, you can't use mount. So some little tidbits there if you're working with this. So in script 3, what I'm going to show is how you can circumvent the basic init startup process by just specifying what you want to go run. And in this case, I'm going to go run shell. So that way I can actually play around with my device.
But you still don't have a TTY. Okay.
But I still don't have a TTY, that's correct. I can get it if I wanted to at this point, but I'm not, I'm not going to because I'll do it a little bit later. The only thing I wanted to point out is, even though we've got our shell, if we accidentally type exit, we've killed our init process and game over. So, reset. Do you want to say something?
No, I was just, I got into QEMU early on because I was listening to kernel developers basically talking about this is the way we can test our kernel builds very easily, and you're showing how that is done.
Yeah.
I just, you're basically doing it. If we get a kernel panel like that, it's a hard boot that we have to do, right? It takes forever for it to get back.
That's exactly right.
For you, it's a couple of seconds.
Yes.
For a kernel developer saying, oh, I messed up something, I need to do a new build and test it out, this is an extremely fast process.
Exactly.
Which is, to my understanding, was why the QEMU project initially came around.
That's exactly right. It's a good point. I probably should have put that in the slide somewhere. Yeah, that is my understanding as well from the QEMU project and just looking at some of the history and stuff. So I guess I'll make this a little more of a full-fledged example by updating our SD card. And all I'm adding are a couple extra commands into a default script, RCS, making that script executable, and then that way we can use the default init process and actually have a more workable example. In script 5, we'll actually finally get something that's a usable system that has an actual prompt that won't die on us. And what we can see is dev gets populated, and all that's happening there is really we're just mounting the nice temporary file system. And you can even power off this machine, which is great. So I hope you got the sense from those demos, even though they were kind of quick, some of them were very boring, kind of like watching paint dry. But it's a very iterative process. It's very much go try this, go find the next failure condition, go fix that, and start over and go again. And as Peter pointed out, QEMU was developed to help solve this iterative process and do it a little bit faster using virtualization technology. Because that's exactly what was happening for a good 15 years before QEMU was workable enough.
So how did they do that before QEMU showed up? I was playing with Linux in the mid-90s, and I did wonder when I screwed up a kernel build and I tried to reboot and it didn't work. It's like fixing it was really painful.
Mm-hmm.
How did the developers do it in a way that they didn't spend half an hour rebuilding the machine every time they
You basically
build?
you have two boxes. One box has a serial cable to the other one, and you have a serial port going out. So you could actually get in and see the kernel, what was going on behind the scene. And if it got stuck, you may actually still be able to communicate on the serial port, depending on what's happening, to get some diagnostics. but it was very technical and extremely, I have all kinds of respect for kernel developers. What they can get out of the stack dump.
So if they screwed up the kernel, they copy a new kernel over that serial connection to try.
So there's actually some parameters you can set up for the kernel to go into debug mode. And so you have a secret key you can enable on your keyboard.
Control says.
And that will give the kernel developer access to what actually is going on so they can get some status. There's also something called kdump today that runs in the background that will initiate when the kernel gets into a panic mode and allow us to get more than just that code dump that gets on the screen, but get enough information of the state and what's going on so a developer can actually see what failed.
Oh, excellent. Thanks. I always wondered if they did that.
And if you have word like grub or library, you just cut it.
Yeah, it's just like, it just makes it like your package. Sorry.
Maurice, that was a great question. So I actually wondered that myself, which is why, or how I stumbled on queuing it, and how I started playing with it. Because right now, actually, I will occasionally have to write drivers, and I need to test it somehow before I actually put it on the hardware. And I really don't want to go through the process of build a kernel, put it on, watch it die, take it back.
Yeah.
You know, and just go through that step-by-step process is just painful and it's very slow. So that's actually what turned me on to queuing in the first place.
And once you have compiled the kernel, the first compile is going to take you forever. But if you just have a single module and you just need to fix that, it's a very fast process you now have for testing. So you can actually automate your testing and set up, try out all of these commands. You can now send information as if a device is acting and see how your kernel reacts to those signals. You can do all kinds of little tricky things for your device developer because it's all simulated. You can send simulated signals as if a device were connected to a computer.
Yep, and I actually leverage that in some of my testing where I work. That's a good point. So I guess the last two slides here are just kind of questions that need to be resolved when you're focusing on creating a distribution for a particular architecture or a particular machine that you need to go run on. Obviously, the target architecture that you need to support is pretty important. What devices you're going to be supporting, what file system types you want. All of these are things that are part of, I guess, parameters that go into building your kernel, and also that could eventually affect the distribution decisions later on that you have to make. In particular, what do you want to do after you get up running, and what kind of things do you need to start? What resources will you need? And I want to kind of call out this one project out there called Yocto, that their whole mission right now is actually giving you a very simple way to build your own distribution and to make embedded very easy. They use this tool called BitBake that takes in recipes to cook, if you will, binaries, including generating an entire distribution start to finish that, just as I was talking before, you take an SD card, pop it in, burn it to the SD card, pop it out, plug it in, you're good to go. They make this very, very straightforward and simple. I recently just discovered this. I was thinking about maybe doing a talk on them a little bit later once I understand all the insides of it. So as far as, I'm actually wrapping up a little early. I knew I was supposed to talk for maybe like an hour and a half, but I wanted to run through this a little fast because I saw I was losing some people out there. So
you didn't ask a question early on that I think to me would be interesting. How many people have done just compiling, use a compiler and actually deal with the CPU at that level? How foreign is what we're talking about here?
Yeah, so I was wondering that myself. I probably should have sent an email out to the list. But how many people have not ever compiled programs? I guess might be a more interesting question.
No,
Raise your hand high.
Be
proud.
Not ever.
But not the one.
Not ever.
Yeah, that's a good point. Yeah, because I was trying to balance making the talk interesting for beginners, but also experienced people alike. That's actually a very hard thing to do. But hopefully you walked away with, for those of you who have not ever compiled something, have walked away with a little sense of what's going on behind the scenes.
So one of the things I was thinking of is why would anybody care about this, and where is a practical or real world way to do it? And what I was thinking is, so this week, I think it was this week, I know one of them was at least this week, but definitely within the last 2 weeks, there are 2 Raspberry Pi things that were discussed on lists I follow. One was making basically Google Glass, that someone used a Raspberry Pi to do that. And then it said something about without camera up, or something. I didn't read the whole article. I tend to get, with my news reader, I usually read the subject or the article title and maybe like the first couple words, and that's about it. That was one. The other one was using a Raspberry Pi as a portable gaming device. And they took some, I couldn't tell exactly what the controller was that they hacked with a little LCD screen in it, but it looked kind of cool. But what you could do with this is you could get whatever that Raspberry Pi distro was and use QEMU to fire it up and then interact with it to sort of see how it works. So if I wanted to do development on a Raspberry Pi and I didn't have one, or I didn't want to get another card or whatever, I could very easily start playing around and see what's going on. So it gives you the ability to do development without hardware. Specifically if I'm building software and I'm building it for Linux, but I want to make sure it also runs on a Solaris box, right? For some reason, I would be able to actually use QEMU to fire up a Solaris distro and to test it, right? Same with Windows, same with everything else. So it's very quick and easy. And I'm sure QEMU still does it, but it can emulate mainframes. So not everybody, nobody, hardly anybody has access to a mainframe, but you may need, for whatever reason you wanted to test or to be able to play around with it. This gives you the ability to be able to do that. It's dog slow, or turtle slow, I guess I should say.
Yeah.
But it allows you to play around and to see different hardware. So, from that aspect, it's pretty nice. The other thing is, instead of having, I don't know about you, but I will get frustrated if something crashes and I got to reboot the darn thing. But if it's just an image, that's pretty easy to do, right? Versus if I'm working on the Raspberry Pi. So who here has worked on the Raspberry Pi or some little device that requires an SD card or some other thing? So now I burn an SD card, right, or copy to the SD card, plug it in, it doesn't boot, doesn't work, go back, try it again, and you're going back and forth, and depending on what you're using for displaying keyboard and mouse and whatnot, it can get tiresome and you can get frustrated very quickly. But imagine if I could take that SD card, burn it to that SD card, and then mount it and see, yep, it mounted, it booted up, everything's good. Okay, now I can go to my Raspberry Pi. For instance, one of the things that I was doing and playing with was Pi main, which is, and I got Pi main to boot and come up, but none of the, I think it gives you one test game or anything, But playing with and copying stuff over and dealing with it's a pain in the butt. I'm probably going to use QEMU now to boot up off that SD card, copy a couple files into it, and now I can take it over to my Raspberry Pi and actually have a more working, whatever the right phrase would be for that, but to have something that's actually useful. So that's sort of how or why I would care about that sort of thing, play around.
I guess another thing I should point out is Android, the emulator that they provide, if you're doing Android development, is based on QEMU. And you can actually, as a GUI designer, play with lots of different layouts and stuff and interact with the image directly.
I mean, this is the chicken and the egg, right? How do you get on a processor the first time? I mean, how do you get the OS on it and all that? This
Exactly.
is, without technology like this, you wouldn't be able to.
Exactly.
So yeah, I mean, whole Android development is an actual excellent point. It gives you the way, and that's how 3 summers ago, 3 summers ago, I guess, when I was working, we were doing some Android development around the NFC chip. just making sure that the thing booted and came up. It was very easy to use this instead of rooting and doing all sorts of crazy things to my Android device.
Yeah.
So it did make it easy.
Greg,
Yep.
I'm probably the least technical savvy guy in this room, okay? But another example of I think what you're talking about here is this device right here. It is an emulator. It's emulating the internet. Okay,
Different. And what I want to do is, because we're going to have some time, is see if we can fire that thing up and take a look at it so everybody gets a better idea of what the internet in the box is and what Penny's looking for possible help with. And
But
so,
what we
We have
have,
some more questions about this presentation.
yeah, absolutely. Yeah.
but if you just ignore the content of the box, the data,
Yeah,
from an operating system point of view, the small operating system that's in this thing here is emulating the internet and is trying to do something in a different way.
I think
Right?
I can see that.
Instead of sending you out to the internet, it's saying go to the box and get all this stuff.
Yep.
So there's a way of improving that.
Yeah, I think it's probably going to, is it connected via USB or something?
Ethernet.
No, it actually has an Ethernet port on it. So it's a NAS device.
Gotcha. Oh, okay.
Okay.
All right, I got a series of questions. And
Okay.
show you how basic my understanding of what you were talking about is. I presume QEMU is a program that you're running on your program.
That is correct.
Is it totally command line driven or?
Yes.
The only way I've ever interacted with it. Now, I'm not aware that there's a GUI out there for it.
Do you want to take that?
Yeah, take it, Jay. So QEMU is command line only. However,
So QEMU, as you described, it does a lot of stuff, but it is also kind of the low-level software that a lot of higher-level virtualization uses. So in the case of something like Red Hat, we have numerous products that are based on QEMU, and it's often the kernel component it's tied to called KVM. So our OpenStack runs on KVM, which uses QEMU. Our virtualization runs on QEMU, which uses QEMU.
Basically, KVM is underneath QEMU.
Yeah, KVM's different than QEMU.
But,
As I understand it, what you were trying, you have been tasked to develop the software for an embedded system. The hardware does not exist yet.
I don't know if that's.
At least it's not available to you.
it's not available to him. That's right.
Okay, now, how do you tell QEMU enough about the structure of this hardware that you don't have access to make it a meaningful emulation?
Good questions. I actually rely on the developers that are out there who do have their hands on the hardware, who develop models that are then embedded into QEMU. And I leverage the work that they've done.
So bring up the command line.
Yeah, sure.
Type QEMU, do the -m helps that just show. All right, so you see all of those, the leftmost column?
Yep.
So there was someone who wrote an emulator to emulate that hardware and manages all that stuff for you.
So these are cookbook emulations that somebody has developed in the past.
Yes.
And are you counting on one of those being sufficiently close to what you're going to be loading?
You're not counting, you're betting everything that it is an exact emulation and will work the exact same way.
So sometimes, actually, I've been in situations where I have been targeting something that is not specific, but I can get close enough that really it comes down to a matter of tuning parameters. So often I'm concerned with performance. And so I might be compiling something that's tuned for a particular processor, but the only things I have available are what these models have. And some of these models are different processors, but they'll still execute, and that's all I care about, because I might be at that point in time testing the infrastructure, not actually caring about the performance results at that point. What I'm more interested in is the thing booting up? Is it actually starting up everything it's supposed to start? Are those things trying to talk to each other? Because more often than not, they have to. And then if that's all good, I throw out whatever results they're actually generating, because it's kind of meaningless, because the model itself is not going to be as quick as hardware. So I then am able to do my development, and as we have repeatedly said here, take the card, put it in the other box, and then run. And so I'm able to do all the headache work that's walking back and forth, plugging this in, and having to fix little things here and there way in advance. And then I can actually just go run the thing when I finally do get my hands on the real hardware.
Are you able?
Hold on, let's finish this and then we'll go around.
Are you able to put in additional checkpoints that tell you what's going on inside the emulated device, or do you totally have to work it as a black box?
I approach it as a black box more often than not. I am aware that through the monitor you can actually pause the emulation and do some diagnostics on the state itself, which is kind of an interesting concept, but it hasn't come up yet for me in my day-to-day operations. But I know that you can pause the emulation for sure and actually look at the CPU registers, look at portions of memory, and other things to do diagnostics. Does that answer your question?
That did, yes. Thank you.
Clear now?
Yeah.
Excellent. Here, and then we'll go around.
Quick question, what are these written in?
What are what written in? The models themselves, I believe all of them are written in, most of them are written in straight C. And C, yeah.
Just curious.
Most operating systems.
There's actually, what's kind of interesting is more recently I found out Xilinx has put out something called a generic FTD. I believe what that stands for is, I forget what the F stands for, but it's device tree is what the DT stands for. I think it's flexible device tree. You can actually create a device tree binary, which is what the Linux kernel embeds into itself so that it knows the devices it's expecting to work with later. You can change some of those devices, and that will actually change what devices show up in QEMU. And that's on a Xilinx specific image that they put out that is not available in the mainstream QEMU distribution. But I played a little bit with that. So there is some flexibility to it, but for the most part, these things are written in straight C. So.
Again, along the lines, and I'm not sure where you are working in your embedded system, but let's say you were designing a computer for, the 2017 car, okay?
Sure, yeah.
Those devices don't necessarily exist, so they define an interface in software that you talk to. You're relying that whoever defined the interface is accurate, because whatever it's talking to on the other end, let's say it's part of the FOSS system or the environmental, that they're still designing it, but they say, okay, we want it to work like this, so you expect that if you give me an A, I'll give you back a B.
Yeah.
That kind of thing. So then when you actually get to the hardware, hey, here's the prototype car that they've actually built. They plug your software in, and it should work from the perspective that you give it an A, you get back a G. Like,
sure,
right now.
I should.
Well, you didn't read my definition.
You get your waterfall development process going there, and then you get one little change that happened upstream that no one else communicated, and that's usually the cause of all of your problems.
I mean, it's probably in the broader realm of what you're designing.
Sure.
The Linux kernel, for instance, had support for the x86 64-bit processors before the hardware existed.
Yep.
The only way you do that development is on a simulator like QEMU.
So, any other questions on that?
Okay, let's go ahead and see. I'm sorry.
This and
Yeah, go ahead. Well, I don't care. You can leave it on or off. It doesn't matter. But Pete, can you hit the main light in here for me?